So from last week, we have multiplication models. And I went over 5 different models based on some stuff that's in the book and just some general ideas. And typically the first one, it's kind of like the most basic definition of multiplication is the idea of repeated addition. That 3 times 5 is 5 plus 5 plus 5, right? So I have 3 5s added. And that gives me 15. And the reverse of that looks different. So 5 times 3 would be 5 3s added. And so that's 3 plus 3 plus 3 plus 3 plus 3, which gives us the same end result, but it's a very different in-between. And that in-between is pretty important, even though the result is the same. So with that, I'm going to jump ahead a little bit. We have 2 different multiplication problems that have the same answer. The difference in those multiplication problems is the order. And when you change the order of an operation, but the answer doesn't matter, that's what's called the commutative property. So the answer for multiplication is commutative. But the process in between is not. Okay. So 5 plus 5 plus 5 is a different situation than 3 plus 3 plus 3 plus 3 plus 3, even though they have the same total. And this is important to note because a lot of kids are very concrete thinkers and they picture this process as different than that process, even though we later in our lives take it for granted that 3 times 5 is the same as 5 times 3. What do you mean they're different? They're not different, they're the same. No, they are different. And that is important for us to acknowledge. Second model is a little bit more physical than the repeated addition. It's what I call the groups of model. Sometimes it's called the set model for multiplication. And it's a literal replacing the multiplication symbol with the phrase groups of. So 3 times 5 really means 3 groups of 5. And instead of writing down digits for 5, I actually write groups of 5 things. And so I would have 1, 2, 3, 4, 5. There's one group of 5. 1, 2, 3, 4, 5. There's another group of 5. 1, 2, 3, 4, 5. There's the third group of 5, right? 1, 2, 3. And altogether, when I add that up, I get 5, 10, 15 things. Would be the product there, the total. And that's going to look different than 5 times 3, because 5 times 3 would then be 5 groups of 3. One, 2, 3, 4, 5 groups, 3, 6, 9, 12. Still get 15, but it's a different way to get there. So the process of multiplication is not commutative, it's the result that is commutative, meaning we get the same result when we switch the order. But in between, different stuff happens. And these are the 2 most popular, I think, interpretations of what multiplication means. So why is 3 times 5 equal to 15? It's not just because it is, it's because either multiplication means repeated addition or multiplication means groups of, and I can physically demonstrate why it has to be 15. And that's what a model does for us. It explains why we get a certain answer. So those were two of the models we looked at. Some of the other ones, the area model, and with the area model, multiplication is the base times the height of an area. So if I'm again looking at the, let's do the 3 times 5, and I generally view multiplication area as base versus height, and base I would draw horizontally, so the 3 is my base, and the 5 is my height. And so then I want to draw a region that has a height of 5 and a base of 3. So 1, 2, 3, 4, 5, base of 3 over here. So this would be my rectangular region. 3 by 5. And then inside of that, I can see if I split up the 3 and the 5, that I have 15 units inside. And so sometimes we call them 15 square units. Sometimes we just say there's 15 squares. Area ends up giving us squares. Although there are other ways to do area that we'll look at in a future date. So that's the area model. And again, with the area model, I have this continuous area inside. So this whole region here is my answer. And I can count up the squares that are 1 by 1 in there. And we use the area model in conjunction with base 10 blocks for the activity for this section. And we'll review that in a little bit. Very similar to the area model is what's called the array model. And an array is just a rectangular arrangement of things. And a rectangular arrangement has rows and columns, or columns and rows. And so if I wanted to talk about 3 by 5 with the array model, and let's say I was working with coins, then I would have 3 columns, and each column would have 5 rows. So this is a rectangular arrangement of 3 by 5 or 15 objects. So these are discrete things like coins, whereas up here is an area I would paint. Okay, so array is, an area is some region that we can paint, and an array is just a collection of objects that we put in nice rows and columns. And they're considered to be two different models because the area model is what we call a continuous model, and the array model is what we call a discrete model. Like I can't have an area of humans, but I can have an array of humans. Okay? I can't have an area that I paint, right? And then the fifth model we talked about has a couple of different variations. The book presents the fifth one, excuse me, as the tree model, and I also said it's referred to as the Cartesian product model. And some people would argue that these are two different models, but I'm going to lump them together. I did not spell that correctly. There we go. And what this is, it's related to choices. So if you have X choices for one selection, followed by Y choices for the next step. Then altogether, there are X times Y choices for the whole situation. And I can't remember the exact example I gave last time. It was related to something about cars. Let's say it's buying a new phone. And for most phones these days, you have a choice of color. And you have a choice of, let's say, memory or storage. And for color, you know, you could get a white phone, or you could get a black phone, or you could get a red phone. And for storage, maybe you could get I don't know, 512 gigabytes, or maybe you could get like 1024. Maybe I'm off on these numbers these days. I haven't looked at new phones in a while. Gigabytes. Let's say you have 2 choices. So altogether, if you have 3 choices there and 2 choices there, I should end up with 6 possibilities in the end, because 3 times 2 is 6. And the tree version of this is to say, well, let's say first you get to decide whether you want to go with white, black, or red. And then for either phone, you could go with 512 or 1024. So for every color branch, there are 2 more branches for storage, which leads to 6 ends to the branches of the tree. Okay. So that's the tree version of it. If I were to kind of draw it as a Cartesian product, it's going to look a little different, but it's the same idea. Cartesian product just says, just write down the description of each phone. So I would have a phone that's white with 512 gigabytes as one option, or I could have a white phone with 1024 gigabytes for the option. But I could have gone with the black one with 512, or I could have gone with the black one with 1024. Or, you know, I could have gone red, right? With 512, or red with 1024. And they're often listed in parentheses here like points. But these are each of the different results that I get when I follow through one of these branches. So if I follow this top branch right here, that leads to that group of choices, as opposed to following, say, this branch right there in the middle leads to that one right there. So every trace through the tree leads to an outcome. And the Cartesian product is another way of representing those outcomes. But it's a matter of choices. And sometimes this tree model, this Cartesian product, is also known as the fundamental counting principle. When you join a bunch of choices together, you just multiply the total choices to get the end result. And those are the main physical models we have for what does it mean to multiply. Y is 2 times 3, 6. Y is 3 times 5, 15. So that's mostly what we did last week, talked about these different models, and then we played with base 10 blocks. And I'm going to come back to the base 10 blocks in a moment. Based on these models, we get some properties like the commutative property, and then there's a few other. So let's get the boring properties out of the way for multiplication. And like addition, multiplication has what's called the commutative property. And remember, commute has the root, it's commutative, has the root commute, and commute means to move. And that's when you actually physically move the numbers. So the commutative property is that 3 times 5 has the same result as 5 times 3, right? They both resolve to 15, regardless of which model I choose. Then there's the associative property. And the associative property applies to more than two things, and it's the way things choose to associate, right? So 3, 4, and 5 are hanging out together. And today, 3 and 4 choose to associate first before they go and talk to 5, right? But it's not always that way. It could be that 4 and 5 decide to start chatting first, and then they go over and communicate with 3 there. Order of operations says you should do what's inside the parentheses. So this is the first association. 3 times 4 is 12. 12 times 5 is 60. Over on the other side here, the 4 and the 5 chose to associate first, which gives me a 20. And then we go and meet over with 3. 3 times 20 is 60, right? I get the same answer either way. So here I'm kind of violating the order of operations or changing it. So I'm not violating it, I'm changing it with parentheses. And it turns out, even if I change the parentheses, it doesn't matter, I get the same answer. And you may ask, well, so what? Well, it doesn't always work that way. It depends on the operation, right? So just think back to subtraction. We talked about this one last week. With subtraction, if I tried to do something like this, let's write a different set of numbers. Suppose I had 8 minus 5 minus 3, and we throw parentheses in here, which is the way we'd normally do it. 8 minus 5 is 3, 3 minus 3 is 0. However, if we go and change the order of association, so we leave the numbers in the same order, we just say, hey, let's put parentheses here this time. Well, then we're forced to say, okay, 5 minus 3 is 2, then I have to take that away from 8. 8 minus 2 is 6. It is not 0. Okay, so there's no guarantee that operations always associate. And by that, we mean we can change the grouping and it doesn't matter. Sometimes it does. With multiplication, it doesn't matter. So it's said to be associative. With subtraction, it does matter. And so subtraction is not associative. Just to be clear. It is not associative. We looked at these two properties with respect to addition, which is commutative and associative. Another property we talked about with addition is the property of closure. And closure means that if you start in a particular set, you end in a particular set. So, oops, spell that completely, closure. And closure in this case means if you take a whole number and you multiply by another whole number, the result is still going to be a whole number. And it turns out that multiplication does have this property. Any two whole numbers you multiply lead to another whole number. That's not true with subtraction. It is true with addition. Another property of multiplication is the identity property. And so that is this thing we multiply by any whole number, let's say n, and we get the answer to still be n. And so the identity for multiplication is 1. So the number 1, so here's a fancy 1 there. 1 is the multiplicative identity. One times any number, that number is itself. It keeps its identity. Another property for multiplication is the zero property. So if I have 5 groups of 0, I still have 0. Or if I have 0 groups of 5, there's no groups of 5, so you still have 0. No matter what number you multiply by 0 in either order, you always get 0. So any number times 0 is 0. Which is a big deal. Nothing else like that happens in addition. It doesn't happen in subtraction, where the answer is always 0 or always some number all the time. So this is a big, unique thing. Nothing like this happens in addition. Nothing like this happens in subtraction. The consequences for division are fascinating. We'll talk about that later. And then I'm going to return for a moment to the area model to demonstrate another property. And what I want to look at here is, let's look at 3 times 6 as an area. So let's see, 3, there's 3. And then I'm going to come up 1, 2, 3, 4, 5, 6. And then I'm going to just draw a line right there. So on one hand, this is 3 times 6. But with that red line in there, it's making me think, well, this over here is really a length of 2 and then a length of 4. So once I do that, something else is going on. If I look at it with the 2 and the 4, I've now split this area into 2 rooms. So although the base is 3 for both rooms, there's a length of 2 and there's a length of 4 there. Now this bottom room right here, let's make that room yellow. I could describe that room by saying, well, that room right there, it's 3 by 2, right? And this room above, let's make that the green room here. Highlighting. That room up there, it is 3 by 4. So this addition within the multiplication leads to a fascinating conclusion that there are a couple of different ways to look at the 3 times 6, given that 6 is 2 plus 4. I can either view it as 3 times 2 plus 4, which is 3 times 6. Right? Or I could say, well, it's a 3 by 2 and it's a 3 by 4, which expresses it as, let's see, 3 times 2 is 6 on a good day, and 3 times 4 is 12. And that 6 and 12 gives me an 18. Coincidentally, 3 times 6 is also 18. I get the same answer. And this idea that both of these rooms have that same base is what's called the distributive property of multiplication over addition. That 3 applies both to the 2 and the 4 as a multiplication. So the area model shows why we get to distribute with addition. So this is known as, sometimes we just call it the distributive property, but it turns out there are many distributive properties. This one is called the distributive property of multiplication over addition. The multiplication up here jumps over the addition to be carried out on each side of the addition. And that's just a consequence of the fact that multiplication is an area, and we have the same base in both parts of the room. And so that's a very important property, mixing multiplication and addition together. Okay, so we have, let's see, some other ideas to look at, but I think it is now time to take a look at base 10 blocks again. And so what I'd like you to do right now is to consider the multiplication of let's try 17 times 13. Now let's make it a little more interesting. Let's go 23. 17 times 33. And here's what I would like you to do with this particular problem. I would like you to illustrate, means draw a picture, and explain some words using, base 10 blocks and the area model, which could be the array model, depending on how you look at it. Started writing area, then switched to array. Okay. So this problem right here, 17 times 23, with base 10 blocks and the area model, show what the answer is. So this is related to that activity we started last week. I'm going to pause the recording here and continue it in a moment while you all, okay. So here I'm back. Those of you in the future, I was hardly gone. So just a couple of notes on here. I've thrown some work in. At the top, I made a note to myself that multiplication means area. Area is base times height. And I chose to change the order to 23 by 17 because on my screen, it was easier for me to make 23 go sideways. I didn't have enough room to go up with it. And that's okay. So if you do 17 across the bottom, then you have kind of like a flipped image of mine. It shouldn't matter. But the image will look slightly different. So the way these images work is I measure out 17 in one direction. I measure out 23 in the other direction here. And I have to mark off the 10s and the 1. So for 23, I have 1, 2 10s, and 1, 2, 3 1s. And that's important because I'm supposed to use base 10 blocks here. For the 17, I have to clearly show that I have a 10, right? A 10 block followed by a whole bunch of 1s. How many? 7 of them. I'm going to turn off the grid for just a second. All right. So here it is without the grid. So without a grid, it's a little harder to draw to get your lines horizontal and vertical, I find, but it's doable if you're careful. But again, I have a 10 and 7 1s. I have 2 10s and 3 1s. And then what we do is we use the divisions for the 10s and 1s to fill in the grid. Okay. We don't want to mark every single one. If we have a 10, we want to keep the 10 because 10 by 10 gives me this new 100 block here. Right? And that's an important feature of the answer. Regardless of whether I do the expanded multiplication or this carrying version of the multiplication, often called the standard algorithm. Now, once I've got that drawn, inside I have a bunch of hundreds, 10s, and 1s. I start seeing if I can reorganize them. For example, wherever possible, I want to trade 10 1s for 1 10. And I found I could do that twice. So here is, oops, let's switch to a pen. Yellow, for example. So here is one group of 10 1s that I'm doing a trade on. And then I have this other group down here that I'm doing a trade on. Okay. You could have written instead trade 20 1s for 2 10s. That would be cool. But you have to acknowledge that's happening. Okay? Because pieces jumped ship, right? These 1s are no longer 1s anymore. They now live in the 10s column, right? This 2 here, switch to the highlighter. This 2 here indicates I jumped ship there. Oops, my highlighter stopped working. Oh, there we go. Or in the standard algorithm, there's my 2. It jumped to a new column. So I have to account for that in my picture somehow. Okay? Whether I do the physical trade or I just write that it's happening. One of those two things has to happen, but you have to have some explanation. Similarly, these 140 10s up here, I can grab 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and trade them for 100 piece. And that happens here, that 10, those 10 10s jump ship. It's now 1 100. Up here, I carried that 1. Why did I do that? because 10 tens jumped to be 100. They're now in the 100 column. And that's represented here also. Okay. So I tried to use my highlighter to indicate the relation there. If that's not clear, then I need another statement. So if I was going to hand this in to my teacher, would they understand that this yellow highlight there matches that yellow highlight? Or this yellow highlight matches that one? Maybe. So maybe I need to make one more statement to be extra clear. So let's say I pick on this one right here. Carrying the 2, let's see, where did that come from? From 3 times 7 to the tens column. Means I traded 21s for 2 tens. We want to emphasize that physical trade with the carry. Okay, so that's a big part of this right here. So there's 2 big components. Component number 1, can you draw this area right here so that it looks like base 10 blocks? Okay. If you're having trouble drawing it, then switch to the app. So I'm going to check out some of those apps that were chatted in. Let me go find those. Chat apps. So we got a whole bunch. All right, let's pick on Lauren. Beautiful, look at that. Yeah, so there's the 200s right there, and the 3 times, let's see, what was that one? That was, I'm losing my mind here. Oop, I'm missing some of the picture, or is it all there? See, there's a zoom. Can I drag the screen? Huh, some of your blocks ended up off the screen in my version of it, but it's close enough. Okay, so we have our 140 here, right? Our 7 times 2. Okay, there we go. And down here, I was thinking the 3 times 7 is the 21. Yeah, so the only thing this picture is missing is a reference to that we're going to trade these in. So I'm going to make a copy of this just to take it one step further. So that's an awesome start. So sometimes I have 2 sequences for this picture. I have the first one here that gets me started, and then I start trading. So to do the trade, what I can do is just circle a bunch of blocks. So I'm going to circle a bunch of these green ones here, and it highlighted all of them. And then I'm going to say, join some pieces. And what it's going to do is it's going to say, oh yeah, 10 of those right there work. So let's just pull you out of the way. Okay, so that's still 140 here. It's just now a 100 and 4 ones. And I could do the same thing down here. I could take, oops, oh, I accidentally split it. Circle these guys here and join, and then I get 10, 20, there's that one right there. Okay, so there's my 21 right there. But now I can see that I have 1, 2, 300s. That one right here, well, I guess I can't pull that off, is now over there by itself. And then I have 4 10s here, 3 10s there. So there's 7 10s plus 2 more 10s is 9 10s. Okay, so let's get rid of a little bit of text. So that one is not relevant anymore. Neither is the 21. Let me draw with my pen today. I won't do it. I got to draw with my mouse. Darn it. All right, see if I can write as good as Lauren does. So this is a 40 there, almost as good as her. And here's another 100 there. And then I've got 20 over here and a 1. So altogether, it looks like I have 3 hundreds, which I'll write in expanded form like that. And I have 4, 5, 6, 7, 8, 9 10s when I regrouped. And there's only 1 1 hanging out. So then with these toys here, I would do it in 2 stages. The first stage is where I just draw the area. Here's my area. Now to get the answer, I trade stuff. Okay. So I traded stuff. I hate drawing with the writing with the mouse. I traded stuff. Bear with me. Okay. Cool. Let's check out another one. Let's check out what Emma's got. Oh, both. Yeah. So you've got the original drawing here. Okay. And then we've got the trades happen to show the 301. So the only thing missing here is just the explanation, like how do I get from here to there? And so that's where, like if you were using this tool to turn your work, I would then whip out the text tool and start typing out what I did, okay? With the mouse is so painful. So that would just need some text there. Okay, so how are we doing? Does anybody have any questions about Lauren's version, Emma's version, my version? Let's go back to my version. Where's my version? Right there. So again, what I'm looking for in a situation like this is illustration, right? So show me an area with base 10 blocks. Then explain how to turn that into the answer, okay? So I have my trades going on here, and then I show either the expanded or the standard or both algorithms with a couple of sentences about what's going on here. Why did I carry? How does the carrying relate to the picture over there? And this is what I'm looking for each of those problems in activity 3.3. So if you already submitted activity 3.3 and you're like, oh man, I don't think I explained enough, or I don't have both pictures shown, then I think I set it so you could do 2 submissions. Let me go double check that. That is on that page somewhere. Settings. In case anybody wants to resubmit, let's make sure it does not. Let's make another submission there. Okay, so if you want to resubmit, I just put an optional second try in there. So you can go turn it back in. All right, so let me see. Are there any questions in the chat? Nope. Does anybody have any questions about what I'm hoping for about these 4 problems there? I'm hoping for an area along with an explanation. My advice last week when I assigned this was that you show both the expanded algorithm and the standard algorithm to further help explain your answer. You're confused on what trading is needed. Okay. So let us do this problem again in the Math Learning Center, and let me get a new version here. Okay, so here I have a blank screen. Let's move that out of the way, and I'm going to switch colors to this version. So first thing I have to do is build my numbers there, and let's say I do it the other direction. So I'm going to make my base, let's go down here, hopefully I have enough room, of 17. So I have enough there. 1, 2, 3, 4, 5, 6, 7. And let's circle those suckers and move them. Oops, I missed. Darn it. Okay, so I have just measuring out, there's my 17 that way. And then I got to measure out this way from about there, 10, 20, 1, 2, 3. Oops, I missed one. So what I've defined here is the base and height of a rectangle, and the rectangle is going to live inside here. Then I'm going to fill in the inside. So inside 10 by 10 gives me 100. Another 10 by 10 gives me 100. And then over here, I have 10 by 1, and another 10 by 1, and another 10 by 1. And then I got to fill in over this way. So from here, I have a 1 by 10 I need to throw in. So I have a 1 by 10, another 1 by 10. I have 7 of these 1 by 10s coming across the bottom here. And the green and yellow I have on the side are not part of the area, they're just measuring sticks. I'm gonna pull those out in a minute. Just for me to make sure I have this set up right. Right, 1, 2, 3, 4, 5, 6, 7. And then I gotta repeat that group, so I'm just gonna do that the easy way by highlighting them and duplicating them. Get them, almost all of them. Do it anyway. So duplicate, duplicate. Goes there, grab one more. Okay. And then, so this right here is not part of my region. Let's get rid of it. That's not part of it. That was just a measuring stick. Measuring stick. These guys I think I'll steal because I need them to fill in that upper corner there. And then I also want to duplicate them. And let's do that again. All right. And then these guys here need to go away because they were just for me to line up my grid. Bye-bye. Yes. All right, so I just drew a region here that's 10 plus 7, 17 across. Oops, back there. And then I made a height here that's 10, 23. So here's my 17 by 23. But that doesn't, I mean, that shows how to get the answer, but that doesn't show the answer yet. So that's kind of stage 1 here. So I'm going to set up my share on this, copy that so I can reuse it over here. Okay, so stage 1, draw 17 by 23. So there's my first one. Stage 2, now we start regrouping stuff. So how do I get the final answer? Well, the final answer now is I say, okay, well, how many of these guys here are going to make a 100? So I'm just going to count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I am going to trade those in for a 100. So to make that happen on this app, and really I'd rather have you draw this on paper. This app is cute, but I think it's almost a distraction. I use the shift key, so if I click one of these and then hold shift, if I hold shift down, it selects a whole bunch together. So up here, I want to do something similar. I want to find out, are there any groups of 10 up here? Because every time I have a group of 10, that's going to contribute to an actual 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I'm going to trade those in. And can I do that again? I think I can. So 1, 2, 3, 4, 5, oops, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to trade those in too. So I'll make some notes here in a minute, but I traded those in. So now I just want to make a note of what I see here. So I'm going to use the text tool to do that. At the moment, I now see that there are 3 100s, and I see 1, 2, 3, 4 at the bottom, and at the top I see 1, 2, 3, 4, 5. So altogether I see 9 10 pieces, right? Because these are base 10 blocks, and I only see 1 1 there, and so that means my answer must be 391. And again, to make that happen, so I'm just going to move this. Can I move that? Oops, wrong button. There we go. I'm going to move that over here, say. But to make this happen, I had to do some trades. So up here, I had to trade 21s for 210s. So that's what I did right here. And then here, I had to trade 10s for 100 in order to realize that the answer was 391, because it's not obvious the answer is 391 when I look at this picture right here. So we have to actually physically trade. Why do we have to physically trade? Well, we have to physically trade because that's what happens when we do our arithmetic. So let's see, where's my board? Let's try again. Oh, I hid my board. There it is. So new page. So those pictures, let's actually bring them in here. Screen clip this one first. You were there. And then the other one. Oops. Screen clip. There you go. It's making more sense now. Over here. I want a little room in between. So that's the best I got. There. So the big question I'm trying to get at here is when we do our standard algorithm, and we write, say, 17 times 23, and we do something like, say, 3 times 7 is 21, but instead of writing 21 down there like that, I put the 1 there and the 2 there. What gives me the right to put that 2 right there? That gives me the right there, because I'm trading. I'm really legitimately trading in a whole bunch of 1s for some 10s. And then switch color. And then I say, so let's just finish that actually. 3 times 1 is 3, plus 2 is what, 5. Switch color to green. And then I say 2 times 7. That's really 20 times 7 is 140. I put the 4 here and I throw the 1 up there. What's that 1 right there? It's this trade right there. So that's the connection I'm trying to make here. And then we finish it. 2 times 1 is 2, plus 1 is 3. So this is kind of a magic algorithm that produces 390. Why the hell is it 390? Excuse me, why the heck is it 390 or 391? It's because we actually have to trade in 1s for 10s and 10s for 100s. And I want you to be able to illustrate that sequence of events. Okay, so that's what I'm hoping for this activity. And give it your best shot. If it doesn't go well, then I will give you feedback.
So is that the expanded algorithm at the bottom in the second picture? That 3 times 100, is that what you want? 3 times 100 plus 9 times 10? Or do you
this down here at the bottom,
yeah,
that's not the expanded algorithm. That's just the expansion of 391. The expanded algorithm comes from this first picture here. So if in this picture I make a note that I see 200 in this corner and I see 140, oops, 140 in that corner, I see 30 in this corner, and I see 21 in that corner. That is a picture of the expanded algorithm, but here's the expanded algorithm down here, expanded. We write 17 times 23 like we did before. And then I say 3 times 7 is 21, and I just write the 21, right? There's no carrying going on here. And then this is 3 times 10, which is 30. I got to think about place value. And then 20 times 7 is 140, right? So notice I'm redeveloping the numbers that live in my grid there. And then this is really 20 times 10, which is 200. So this right here is the expanded algorithm. And that also leads to the answer 391. Good questions, you guys. Yeah, so we take for granted this process we learned as kids for multiplication. Why does it work? Well, it works because of the way base 10 numbers work, which these blocks illustrate. So I'm trying to get us to rethink, why do we do it this way? So these pictures explain both why the standard algorithm works. They also explain why the expanded algorithm works. Next, we're going to take a look at some other algorithms. All right, so I need to stop the recording.